Basics of hybrid systems. So what are hybrid systems? So unlike systems we've looked so far, like a pendulum or a projectile, they only had one set of equations which describe the motion, which was basically derived from Newton's uh, Euler-Lagrange equations, right? A hybrid system, on the other hand, has different behaviors depending on which regime they are operating in. So the simplest example is, so let me write this down, have different equations depending on which mode they are operating in. Okay, so a simple example of a hybrid system is a bouncing ball. Okay, so let's just try to think what a bouncing ball does. Well, first, uh, let's say there's a ball which is dropped from a height h or y under gravity. So it falls freely under gravity. Then what happens is there's an instant before bounce where it's sort of just grazing the surface. Okay. Uh, so in this phase, the velocity of the ball is y dot. And the way we like to call this in this course is that we'll write the velocity with a negative sign just to indicate that that's the velocity just before bounce. That negative comes for that. Then there's an instant where the ball is switches velocities, right? It goes, the velocity switches from being downwards to upwards. So the ball again, but this time the velocity is upwards, and I'll call that y dot, but I'll put a positive sign to indicate that the velocity is after bounce. Okay, and we'll consistently use this notation, positive and negative, to indicate before and after bounce. Okay, so that's how we describe the motion. How do we actually represent this with equations? Well, first of all, for free fall, we've already used Euler-Lagrange to do that. It's simply the acceleration is negative g. That describes the motion of a ball being dropped. What about the moment the ball bounces with the ground? It turns out that there is a formula which comes from Newton's coefficient of restitution, which describes the behavior of the ball between bounces. Okay, so when the velocity before bounce, which is y dot negative, is related to the velocity after bounce by this factor E, known as the coefficient of restitution, where E is always between 0 and 1. Most likely it is less than 1. 0 indicates it's a plastic collision, which means that the velocity after bounce is 0, it sticks to the ground. While if it is 1, it means that the velocity after impact is the same as the velocity before impact, and that's a perfectly elastic collision. So this is basically an empirical relation which is found for, which is dependent on the surface properties and so on. But this equation here comes from Newton's laws, which is not an empirical relation. It holds true no matter what. Okay, so that's how we describe the bouncing motion. Okay, now before we can actually analyze and simulate the system, let's try to understand how this particular simulation will go. So first we have free fall. Okay, so it's falling freely under gravity. Then at some instant, we have a switch to a bounce. When does the switch occur? Well, it occurs when, in this case, you can notice it's when y equals 0, right? Y equals 0 is the height of the ground, but it could also be y equals some constant value depending on where the ground is. Okay, once there's a bounce, there's again free fall. Then we again with y equals 0, we have a bounce, and so on. So we have free fall bounce, and you can see there's a pattern which emerges, which is basically you just have these two phases. So what we can do is we can identify sort of a building block for uh, describing this motion, which is basically starts, you can either start from here, right, and end right there, or if you want, you could also start it from here and end it there. It's really up to you. It doesn't really matter. Let's just assume that we start the repeating unit here. So this is one bounce. Okay. And we see that this is the repeating unit. So the crux is that if you want to simulate the system of a ball bouncing, then what you do need to do is you need to simulate this repeating unit and just run it into an infinite loop, so it just keeps bouncing. And that's basically what we'll do for hybrid systems. We'll basically identify the building block or one unit which repeats, and then just keep that simulation going forever. Okay, so I'm going to show you code to do this. Now, before I show you the code, there's one interesting aspect here which I want you to understand, which is kind of not the usual thing we do with projectile motion or pendulum. Here, when we simulate the system from free fall to bounce, we have to sort of take the equations, which are these equations, that is the equation of motion, integrate that, and stop integrating when y equals 0, right? So when y equals 0, we stop integration, we switch the velocities based on this condition, and then keep integrating. So what you notice is that this integration from one free fall to the bounce is not is well, it's time. You integrate ahead of time, but your stopping condition is not based on time. You don't stop when it's 5 seconds or 4 seconds or 3 seconds, but you stop when y equals 0. And that is sort of unique to hybrid systems, that there are these things called events. So that's one event when y equals 0, where you need to stop the integration. Okay. Now, normally when you take an integrator, it doesn't have the accommodations to stop the integration when an event occurs. So you can take Runge-Kutta integration, which is typically taught. It doesn't really have that. But ODE solvers in MATLAB actually have something called events inbuilt into their function, which basically helps you to stop the integration when things happen. Like, for example, here we'll make the integration stop when y equals 0. Okay, and I'll show you how to do that. So let me write that down before I move on. So ODE 45 has something called events to detect y equals 0 and stop integration. And this is a feature of ODE45 which we'll use throughout this course to stop the integration. So I'm going to show you all this let me just briefly talk about them. All my main files have this ball main, which is the file you need to run. There is the RHS, which is the equations of motion. There's a file which is about contact, and then there is this one bounce, which is a building block. So let me first, let me just in this case open all the files. So Command A, drop them. Okay, and let me run the ball main file. So in this case, I've defined restitution to be 0.9. Okay, so that stops there. Okay. Um, so what goes in this file is basically you are essentially in this file main you're calling this function called one bounce, okay, which is basically this building block which has two parts in it. One part is it uses ODE45 to integrate the equations of motion using the RHS. The RHS basically just describes the acceleration is minus g, which I wrote down, okay, and then it goes integrating till it needs to detect that the ball is contacting the ground. This happens through this options, okay. If you see the options, there is the thing which is relative and absolute tolerance, which I've been using for each and every of these files for OD45. But there's this thing called events, which says events at contact. So contact is the event which it's looking for. So this event function has these three things which need to be defined no matter what you do. You need to define what is known as a G stop, and I is terminal, and then a direction. Okay, and I'll explain what these three things mean. The G stop tells you exactly when you want to stop. In this case, I want to stop when the height in this case is described by the position of the ball minus ball dot ground. Okay, ball dot ground is basically the height of the ground. Okay, in this case, I actually did not put it zero. I actually put it at, if you look at ball dot ground variable, it actually is minus 0.175, and I can tell you why I did that. If you look at if you look at this figure, uh, I need to put it slightly down, not exactly at zero, because this ball has a finite radius. And otherwise, if I put it at zero, then it will look as if that ball has penetrated the ground. So I actually manually adjusted this to be 0.175. It just looks right for the animation, because that's the first part of contact. The second part of contact is the direction. So when you specify that the ball has to hit the ground, you need to specify which direction the ball needs to go. Now, one way the ball can go is it can go inside the ground, in which case the direction of y is negative, or the velocity is negative, and that's why I said negative one. The other case which this can happen is if you throw a ball and there's a ceiling, and if the ball crosses a ceiling and the ceiling is at some height, say 5 meters, then in that case that crossing is going to be positive because the velocity is positive. Okay. The third thing you need to specify is terminal. This is basically specifying when you detect the event that y of 1 equals ball dot ground in this direction, should you stop or continue integration? So if you want it to stop, then you put 1. If you want it to not stop, then you put anything other than 1. Okay, so those three things define how you're going to handle the event, which is the ball hitting the ground. Okay, this is kind of very crucial. People, students don't get this, but you want to remember this is a fixed format. You have to use the same format. You can look at the documentation of ODE45 if you want more information. Okay, so that's the bounce. As I said, it has those two ingredients. So that's OD45. Then once you detect the ground, it basically stops integration. Then it basically keeps the position the same. So the end position the same as this new start position. And then the velocity, however, reverses. It becomes negative e times the old velocity. This is just writing the restitution equation. And then there's some bookkeeping on to keep track of the position. I need to keep track of the position at every of these loops, right? So this is basically, let's see, this loop is running from t0 to t end. So when this loop runs, I need to keep track of positions, and that's some bookkeeping I need to do. And then finally, I do some plots, and then I do the animation. So let's run this again. Okay, stop. What I forgot to show you is the plots. These are the plots produced by the graph. So you can see the position, it's parabolic, and then the velocity is more or less well, it's constantly decreasing, but then it switches exactly when it hits the ground. Okay, so that's the basics on simulating and understanding a hybrid system.